So let's take a look at work problems. So for number one, find the work done by pushing a car 8 meters while exerting a constant force of 900 newtons. So in order to solve this, we need to know that work is equal to force times distance. So notice we're given a force of 900 newtons and we're trying to push the car 8 meters. So all we have to do to solve this is multiply the force 900 times 8. And so the work being done is 7,200, and the unit for work can be Newton meters, because notice we multiplied newtons and meters, which is equal to joules, so 7,200 joules. And another form of work, or another unit of work, can also be foot-pounds. So keep in mind that you always have to have the units in newtons and meters or feet with pounds. So you cannot have newtons with centimeters or newtons with inches. It must be newtons with meters. And the same thing goes with foot-pounds. So now on to number two. A force of 10 pounds is required to hold a spring stretched 4 inches beyond its natural length. How much work is done in stretching it from its natural length to 6 inches beyond its natural length? So the formula for spring force here, so we'll call it f of x. F of x is going to be equal to k times x. K is going to be a spring constant, while x is the distance the spring is stretched beyond its natural length. And so the work is calculated for the spring by taking the integral of f of x. So basically, we're going to take the integral of k times x to get the work. So in order to find what k is, we can use this top equation here, because it has already given us a force of 10 pounds, and that 10 pounds is required to hold a spring stretched 4 inches beyond its natural length. So if f of x equals 10, so we get 10 equals k times x. Now if x is the distance the spring is stretched beyond its natural length, and we say that it is stretched 4 inches. Now remember, we need work to either be in foot-pounds or in newton meters. Since we're already given pounds here, we need to change inches into feet. So 4 inches, basically 4 over 12, is a third of a foot, so x is going to be 1/3. So k times 1/3. Which means that k is going to be equal to 10 divided by 1/3, or 10 times 3. So k is going to be 30. So now we can evaluate work here by taking the integral of k times x. So we're going to take the integral of k, which is 30, times x dx. And for our bounds of integration, notice we're trying to stretch it from its natural length. So its natural length is basically going to be 0. And we're trying to stretch it 6 inches beyond its natural length. So we're going from 0, now 6 inches, we need to convert that once again to feet. 6 inches is half a foot. So we're basically going from 0 to 1/2, the integral of 30x dx. So the integral of 30x is 30x squared over 2, or 15x squared. And we're trying to evaluate from 0 to 1/2. Now when I plug in 1/2, we'll get 1/2 squared, which is 1/4, minus when I plug in 0 to x squared, and 0 squared is 0. So we'll get 15 times 1/4, or 15 over 4 foot-pounds of work needed to be done to stretch the spring 6 inches beyond its natural length. So now on to number 3. An aquarium 2 meters long, so write 2 meters long, 1 meter wide, and 1 meter deep is full of water. Find the work needed to pump half of the water out of the aquarium. The density of water is 1,000 kilograms per meters cubed. Now, whenever it gives a problem where it asks for the work given some sort of density, we most likely have to use this equation, where the work is going to equal, the work is going to equal the density times the force of gravity. So that those together multiply will give you the weight density times the integral from a to b of the area, the cross-sectional area in terms of y. If we're integrating with respect to y, then it'll be in terms of y, times the distance the cross-section needs to travel, times the thickness, or dy. So we've already identified that density is 1,000 kilograms per cubic meters, and we know that the force of gravity, or acceleration due to gravity, is around 9.8 meters per second squared. So I will sub in P and G into the equation, or into the integral formula. So the work is going to equal 1,000, the density, times the force of gravity, 9.8, times the integral. Now we need to find out our bounds, the area, the cross-sectional area, and the distance the water needs to travel, since we're trying to pump out half the water out of the aquarium. So let's just go ahead and start out with the cross-section. So let's say I take a cross-section of this aquarium here, just the middle portion. So if I took out this cross-section, it would look something like this. So the thickness is obviously just dy, because the cross-section is dy thick, as shown up here. That is going to be part of our formula. And so we know the aquarium is 2 meters long and 1 meter wide. So the area of this rectangle is just 2 times 1, or 2. So that will be our cross-sectional area, 2 dy, and I'll add dy later. So now, in order to find the distance the water needs to travel, I will put this front face of the aquarium in a coordinate plane. So if I draw a quick coordinate plane here, this will be the front face of the aquarium. And notice that it says the aquarium is full of water, so it's covering the entire thing. So we're going from basically 0 to 1. The height is 1. But realize that we only need to pump out half the water. So we only need to go halfway up. So from 0 to 0.5. Which means our variable, or our bounds of integration, our lower bound A, is going to be 0, because we start at the origin here, 0. And we're only going to go up 0.5. So that is going to be our top bound. And so for the distance is basically going to be equal to the top bound, B, minus y. So if our B value is 0.5, then our distance is going to be 2. Well, 2 is going to be the area, but our distance is going to be multiplied by 0.5 minus y, and dy. I'll add it last. And so if I were to multiply the 1,000 and 9.8, the final formula here is going to be 9,800 times the integral from 0 to 0.5, or 1/2, of 2 times 0.5 minus y dy. Since 2 is a constant, I can also bring that outside the integral, but when you calculate this, you should get exactly 2,450, and the unit for this is joules of work. So now for number 4, the tank is full of water. Find the work needed to pump the water out of the outlet. And it gives us water weighs 62.5 pounds per cubic feet. So once again, the work formula here, when it gives us a certain density, work is going to equal to density times gravity times the integral from A to B of the cross-sectional area function times the distance function. And on the previous problem, I just realized instead of having dy, I had d of x, so for my distance function, so I apologize for that. Instead of d of x, it should have been d of y. So we don't need that because we're integrating in terms of the y variable. So this problem is a little bit different because it's giving us a different weight here. We're given 62.5 pounds per cubic feet. So notice pounds is a unit of force. So in this case, we don't even need to multiply by gravity. Now in the previous problem, we had kilograms, and kilograms is not a unit of force, so we must multiply by gravity to give us a weight density. In this case, this is already giving us a weight density, so we don't need to multiply by gravity. So if I were to pick out a cross-sectional area of this tank here, it looks something like this. We take out a rectangle. So we already know the rectangle's area is going to be width times length. The length is obviously 8 feet, but we need to know what the width is. And so if I were to put this front face in a coordinate plane here, so we know we can just draw a simple triangle here because we need to know this distance. We can pick any cross section. Well, let's just pick this cross section here. Now we know the radius, the distance from the outside to the center, is 4 feet divided by 2. Since 4 feet is the diameter, so we know that the radius is 2 feet. So that is going to be the hypotenuse of this triangle here, if we draw a triangle. Now, this distance we need to find out, so we'll just call that A. And then for this distance, notice the top bound is 2, so that the length of this triangle, or the length of this side of the triangle, is just going to be 2 minus y. So remember that a squared plus b squared equals c squared. So using the Pythagorean theorem, we can find out what a equals. A is going to be equal to the square root of c squared minus b squared. So a is going to equal the square root. Now c squared, if our hypotenuse is 2, 2 squared is 4, minus b squared. So if b is 2 minus y, then b squared is 2 minus y squared. So once again, we got 2 minus y because we've taken the top bound here, which is 2, and we're subtracting the y distance. So that's why the side is 2 minus y. Now notice a is only half of the length. We need both of the lengths, so we're just going to multiply by 2. So our area in terms of y is going to be equal to the length times the width, and the width is this square root times 2. So 2 times the square root of 4 minus 2 minus y squared times 8, our length. And so for the a and b bounds, the tank can only be integrated from its most bottom bound, which is 0, to its topmost bound, which is 2. So a is going to be 0 and b is going to be equal to 2. But the distance is a little bit different. So the distance formula here, now notice it needs to go out of the outlet, and the outlet is about a foot above the tank. So if I draw the outlet here, the outlet is going to be an extra foot above. So I just cleared everything out here. So the outlet, once again, is about a foot above. So if this point here, if this is 0, this is 2, and we're going up of another foot, then that top value is 3. So we're basically going to go, the distance is going to be equal to the top bound minus y. So 3 minus y. And so when we put everything together, the work is going to be equal to the p-value, or the density, which is 62.5 pounds per feet cubed, multiplied by the integral from a to b. So from 0, which is the bottom bound, to the upper bound of the area function. And the area function, 8 times 2 is 16. So we get 16 times the square root of 4 minus 2 minus y squared times the distance function, how far the water needs to travel. It needs to travel through the tank and up another foot to get out of the outlet. So we go 3, the top bound, minus y dy. And when you use your calculator to figure out the answer, it should give you around 5,808 foot-pounds of work.